Welcome everybody to PyData Global. The presentation at this time is from Francis Alted, and I hope I pronounced your name correctly, Francis.
Yeah.
The title is Introduction to Blosc 2. I'm probably mispronouncing that. An acronym of some type, I'm sure. The next generation of the Blosc compressor. And Francis has worked for more than 30 years in IT and scientific computation in academia, as well as industry, and is now a freelancer. So with that, I'll hand it over to you, Francis. And just FYI, everybody will be taking questions at the end of the session.
Okay, thank you for the introduction. Hi, everybody. Just a quick correction. I am not a freelancer anymore. I am currently working for the Blosc development team, but also I am CEO of ironArray, which is an assay library for competing with compressed data. Okay, having said that, welcome to the talk. I am going to describe the next generation of Blosc, which is fast, compressed, and persistent data store. Yes, Blosc 2. Okay. Now, first, a quick historical introduction. So back in the 1940s, Claude Shannon invented a way to measure the information content of a message and call it information entropy. In theory, you cannot compress a dataset beyond that entropy. And the formula, it's very easy to understand. Just the P sub I means the frequency of every symbol in a message to appear, right? So even if Shannon stated that you cannot compress data beyond that, he did not take into account that symbol ordering, and not only the probability of occurrence, is important when finding ways to express messages in less space than such information entropy. In that sense, Blosc comes with so-called filters that are about reordering data before the encoding stage. One example of this is the shuffle filter. I am not going to enter in the details how it works, but it is just about reordering data in such a way that it benefits the compression ratio when the codecs are trying to compress the data. Okay, and this kind of reordering typically allows codecs to go beyond information entropy limits. So we are all the time breaking entropy limits because of this reordering thing. By the way, Blosc 2 comes with optimized versions of the shuffle filter for not only for Intel but also for ARM and PowerPC. So this kind of reorderings are extremely fast. So what's Blosc? Well, Blosc is all about sending data from CPU to memory and back faster than a memory copy. It typically works by splitting the data to be compressed in blocks for better cache use, and using the typical divide and conquer approach. So every of these blocks goes to the L1, L2 cache, and it is compressed completely in cache. And then when it is compressed, it is stored in the Blosc container. So all the data is compressed here. And of course, Blosc can use different filters like shuffle, bit shuffle, and also different codecs, like LZ4, LZ, LZ standard. Of course, there is a way to leverage Blosc correctly. So typically, the way you do that is to decompress and operate in private caches for best performance. So for example, in this Blosc container, typically you decompress every block internally in L1 or L2 caches. This is important. L1 and L2 are typical private caches in CPUs, especially Intel CPUs. And it is important in order to avoid contention in Blosc multithreading, as we will see later. And the idea is to leverage all the data that is uncompressed in these caches and perform the operations. So for example, in this case, we are performing a reduction when we are computing the sum and then we are aggregating all the sums for all the different blocks to a total sum. So this is the typical way to use Blosc in order to avoid data to travel uncompressed to memory. Okay, so with that, Blosc is able to break memory walls in many different situations. So for example, here it's a plot where we are computing a reduction. In blue, we have the bars where we are computing the reduction in uncompressed state, okay? And we can see that we have a bottleneck here when reaching 12 threads, okay? And that means that with 12 threads, we are reaching the total memory bandwidth on this machine. However, when working with Blosc and doing the same operation, we can see that when we throw more threads at the task, we can see that we can get faster speed than using uncompressed data. So this is the typical kind of accelerations that you can see with compressing with Blosc. Of course, this is real data. This is data coming from precipitation, and the total size is less than 400 megabytes. You can see more details on this blog post here. And then here we can see another plot in the x-axis. We have the time in seconds for doing these operations, where A, B, and C are different arrays. And we are computing the average, the mean of all the arrays. And every array is 3 gigabytes in size. So the outcome is also near 3 gigabytes in size. So in green, we see the memory used by NumPy and the time used by NumPy. Then using Numba, that can do faster operation because Numba can do operations in doing parallelism. And here we can see ironArray, which also leverages Blosc that can perform this operation using compression. And we are getting better performance than Numba because we are dealing with compressed data and we are not hidden by the memory bandwidth bottleneck as much as using data without compression. Okay, so where is Blosc used? So Blosc is used in many places in the PyData ecosystem already. So a lot of people here will be using HDF5 via H5Py or PyTables. Both can use Blosc. Also, ZAR uses Blosc by default via the numcodecs package. And also ironArray is using the next generation of Blosc. So that means that lots of terabytes are compressed and decompressed on a daily basis. And that means that it's quite well proven for the last 10 years. So what's Blosc 2? So as I said before, it's the next generation of Blosc. Essentially what Blosc 2 adds is a 63-bit container called superchunk that expands over the existing 31-bit containers in Blosc 1. So this is the superchunk, and here's the sequence of chunks. These are Blosc 1 chunks. And we can complement all this data with so-called metalayers, which are essentially metadata that you can add to the superchunk. There are two kinds of metalayers, fixed length and variable length, with different properties. Okay, so let's focus more now in the new features of Blosc 2. Like filter pipeline, serialization format, parallel I/O, and pluggable codecs from filters. There are more features, but I think these are the most important ones. So let's start with the filter pipeline. So the compression process, how it's implemented in Blosc 2, is that here we have the original data to be compressed, and then a prefilter, which is a filter that is defined by the user. If he or she wants, Then it creates a temporary buffer, which typically fits in L1 and L2. And then it comes the filter pipeline, which is composed in this case by shuffle and this other filter, which is called NDSIL for n-dimensional rearranging. And the user has also registered a new filter here, which is called UR-filter1. And this can be defined by the user. More on this later. So we create the final temporary that is still in cache. And then finally, the final step is the actual compression via the codec. So we are creating this buffer here, which is smaller than the original one. And then for the compression process, the process is the same, but in the reverse order. So starting from the compressed sources, we recreate the different temporaries, and in order to recreate the original data at the end. So that filter pipeline is about concatenating or composing filters and codecs. And as I said before, Blosc, it's all about reordering things in order to help codecs to compress better. So this is a very important part of Blosc 2. A few words about the serialization format. So we have seen that that we have super chunks in Blosc 2, and there are two ways to serialize them. One is the contiguous frame, and then there is the sparse frame. The difference among two is that the contiguous frame, everything is stored on a contiguous area, either in memory or on disk. Whereas the sparse frame, everything is stored, all the metadata is stored in one single area, contiguous area, but the chunks are stored in different sparse, in different files or areas, either in memory or on disk as well. The frame specification is very simple. We are quite proud of that, and it's fully documented in less than 700 lines of text. So that means that it is very easy to replicate the format. So that this is important in terms of portability, but especially safety, because it's very easy to grasp what the format is about. And one of the reasons for the simplicity is that the format rests on the shoulders of MeshSpack, which is an efficient binary serialization format. Parallel I/O. So for those of you that know Blosc has always been multi-threaded. So there are different threads that take responsibility for compressing different blocks. So the compression process works like this. Then there's the filters pipeline, and the codec. Everything is going on in parallel inside Blosc. And then everything is written in the frame, either on disk or in memory, okay? And that means that if the frame is on disk, for example, that means that data can be stored in parallel, can be written in parallel, okay? And for the compression, is the same process. We start with the frame, either on disk or memory, and then with the codec, the data, filter pipeline, and then the post filter. And everything works in parallel, as I said, which is an advantage. If you combine this with Blosc mask Blosc mask, then you can have a very efficient way to retrieve the data you are interested in. So for example, here we have 16 blocks in a chunk, and let's suppose that we are interested just in the blocks inside of the square, of the red square. So we define the Blosc mask out, okay, where we say Blosc that we are not interested in these blocks, and then Blosc is in charge of decompressing in parallel the blocks that are interesting for us. And this is especially effective when retrieving slices in multidimensional datasets. So the typical way to decompress data or parts of the multidimensional datasets in other libraries is that you decompress the chunks completely. However, if you are interested just in one single hyperplane of this data set, multidimensional data set, that means that you have to decompress much more data than you are interested in, right? Whereas if we have in Blosc 2, we have masks, and we can decompress only the data that is more interesting for us, okay? And in keeping also the parallel properties of ironArray. So both Caterva, which is open source, and ironArray supports this efficient way to retrieve data. Here we see as the performance for slicing in different a three-dimensional array in different dimensions. And we can see that in this case, ironArray can be faster in general than ZAR, for example, that is using Blosc as well. Except for the dimension where it's already in this dimension, if it is optimized for the chunk, in this case ZAR is more efficient. So it's kind of a trade-off. In general, you can get better general performance without worrying too much in optimizing for getting slices in a specific dimension. You can see more about this in this tutorial. Okay, and let me finish this overview with the pluggable codecs and filters. So in Blosc, there is a filters registry. In yellow, you can see the filters registry that are official, but the users can also define their own filters. And the way to define the filters is just to declare the filters and then register the filters using Blosc to register filter. Once the filter is registered, then it can be used in the filter pipeline of Blosc. And the similar procedure goes for codecs too. So people can come and start producing their own filters and codecs on their own, and they can register in Blosc too, and then start using it. However, the most important application of that is that the plugins can be also registered centrally. And that means that when a user has a plugin, typically they can send a GitHub pull request to the Blosc development team. And then the Blosc development team does the evaluation process, and it fulfills all the specs. It goes straight to global registry. And if don't, the original user is informed about this. And in order to restart the process and to fulfill all the specifications for registering the plugins that are stated here in this URL. Registering the plugin centrally, it's very important because that means that there is an easy way to deploy user filters. So central registered plugins are included and distributed within the Blosc 2 library, which can be installed using the Python wheels. So after this operation, just pip install Blosc 2, then all the officially or the central registered plugins are available. And this is a very convenient way to make your filter and codec accessible for everybody. Other features for Blosc 2, safety and security is very important for us, and we are actively using the OSS Plus service for uncovering programming errors. It's a Blosc 2. There is a nice markup for documentation. We are very proud of how nice it looks like, the documentation, which is very important for us. Also, there is an efficient support for the special values, which is very important or really useful for storing sparse data. So, for example, when there is a lot of zeros, this is there is an optimized path for that. And also there is a Python wrapper for Blosc 2 that we recently released, version 0.2. So to conclude, adapting compression, Blosc is all about adapting compression to your needs. So in general, tackling compression includes a gazillion ways to do it, but basically what you are after is to get the maximum compression ratio, but at the same time to reduce the compression and the compression time to a maximum. And Blosc comes with a rich set of codecs and filters that users can easily try to find the one that better fits to their needs. Then Blosc is in charge of orchestrating these codecs and filters for both parallelization and also reusing and sharing interval buffers for optimal memory consumption. And the result is a highly efficient tool for compressing your way. Let me finish with this strong statement, because we think that data is the most important part of your system. And the Blosc development team is committed to the future of your data in that, first, Blosc has a very simple format and hence is very portable and maintainable. We also have spent quite a lot of energy keeping it orderly and clean. And last but not least, safety and security is paramount for us. And in our opinion, proactivity should be the primary mechanism for data integrity. And we have specific pipelines in the continuous integration for ensuring the safety of the format. Of course, I would like to thank all the Blosc development team. Without them, we could not present this or introduce this new version of Blosc. And especially thanks to donors. Without them, we could not have possibly put Blosc into production status. So Blosc came out in just a few months ago in June. And now it's version 2.0.4, which is really meant for production. So yeah, that was my presentation. Thank you for attention. And if you have some question, I will be happy to take it. Thank you.
Thank you very much, Francis. Really, really interesting. I didn't know anything about this type of this field, and I'm not sure whether I know too much more, but certainly know where to look now. There is a question from Richard Pelgrim. He is asking, what about the comparison, I guess, of Blosc to descarrays?
Yes, we have some comparisons about descarrays. Descarray is mainly an abstraction, right, on top of the implementation. So Blosc containers can also be used by Dask without any problem. I mean, Blosc 2 is quite similar to, it's just a format, and Dask can be also on top of Dask. Or Dask can be on top of Blosc. So for example, here we are evaluating a transcendental expression. Okay, and we can see here ironArray versus Dask in both time and memory consumption. In general, ironArray is very much into optimizing not only the time but also the memory consumption. Many times, consuming too much memory is also a bad thing, because it makes your programs slow down a lot.
Okay, well, thank you very, very much, Francis.
Mm-hmm.